Cool. Thanks everyone for coming. Yeah, we're super excited to be here. So we'll go ahead and get started. So my name is Angel Lim, and I'm an engineer on the Voyage inference team. And I'm joined today by my colleague Andrew Gott, who's an engineer on the Voyage research team. And we're super excited today to walk through the Voyage inference platform. This system is responsible for serving all of our state-of-the-art embedding and reranker models in production. Before joining MongoDB, Andrew and I were founding engineers at Voyage, where we built the inference platform from scratch and helped, along with many others, to scale the platform into what it is today. So again, thanks for everyone for coming, and let's just dive right in. So a quick agenda for today. The talk's going to be split up into roughly 4 parts, and we'll make our way top-down through the system. We'll first take a step back and discuss some of the core challenges we face when developing an efficient inference platform for embedding and reranker models. And then we'll dive into our query routing layer and see how we optimize it to hit our strict latency SLOs. And then next, we'll touch on aspects of our infrastructure and see how we optimize our GPU cluster for high throughput. And then finally, we'll take a deep dive into some GPU performance optimizations. Cool. So first, I wanted to take a step back and just discuss some of the core challenges we faced. The defining constraints when developing an efficient inference platform for embedding and reranker models is that the vast majority of our synchronous requests operate under strict latency SLOs. This is because these requests lie on the interactive retrieval path for many of our customers. And so any inefficiency or tail latency is immediately visible to their end users. When thinking about latency, we can basically distill it down to 2 fundamental parts: overhead plus GPU compute. And overhead is essentially all like non-useful or non-essential work so that your infrastructure might have to do. So for example, like request routing or autoscaling, GPU node bring up, and so on. And since these interactive requests tend to be small and latency sensitive, it's difficult to amortize away or hide these overhead inefficiencies. And so to achieve low latency, we've been really diligent about optimizing our infrastructure and removing overhead and also being as efficient as possible in executing requests on the GPU. In addition to latency, just like any other efficient inference platform, we still seek to optimize the global GPU throughput of the cluster. And you'll see examples of this later in the talk. There's a natural tension that arises when trying to optimize the latency of a single request versus also trying to optimize the global GPU cluster throughput. And one last challenge I wanted to mention is that in production, we serve many different embedding and reranker models, fine-tuned for various use cases. And workloads across these different models tend to be unpredictable, bursty, heterogeneous, which further stresses our infrastructure. So as we go through this talk, these are the core challenges and constraints that will motivate different trade-offs we make and also design decisions that we've decided on.
Yeah, so maybe first we can talk about queries and reranker. So these are going to be latency sensitive. And so the first thing is I'm going to use this for illustration purposes throughout the talk. Basically on the left there's a queue, and on the right there's some model replicas. They're all the same model. And those things on the queue are messages, and the models will consume them and then do inference on them. So when you send a request to an embedding model, you give it some text. We might enqueue it as in tokenized form, and then the models will consume it off the queue and then do the processing. So I'll be using this throughout the talk, but yeah. So the first thing is dynamic query batching. So what is a query? So when people are indexing vector DBs, they usually index the DB and then query against it. And the query is what we're talking about here. And it's usually pretty latency sensitive because you're trying to search against the DB, and it's at inference time, and it's getting added to the latency the user sees at the end. So how we define a query is when we get a request, it has a list of examples, each of which can be processed independently. And we define that as the batch size, as the number of examples. And then each example has a certain number of tokens, we call the token count. So a query is a request that's batch size 1, token count less than 512. So it's like a single example, and it's pretty short. And so the thing is that for really small token counts, actually, on the GPU, we are what's called memory bound. That means that we're not actually doing enough math per memory byte transferred to properly utilize the cores in the GPU. And what happens is the latency is almost the same throughout the entire memory bound regime. And you can increase the arithmetic intensity, i.e. the number of flops done per memory byte transferred, by just adding more tokens. And so actually, you can add those tokens pretty much for free. And so we'll see how that affects the end user latency right now. And for now, let's talk about, let's use these numbers to denote the number of token messages on the queue. And what we're going to assume here is that inference takes 1 second if you're processing less than or equal to 4 tokens, and is linear otherwise, 1 second per token. This is just for illustration purposes. It's basically illustrating what we just showed in the slide previously with that graph. And so if we didn't batch anything, the first thing that would happen is all 3 of these model replicas would grab 1 token messages off the queue. It would take 1 second to process, and then after waiting, the next 3 messages would be processed. But because there's no difference between doing 1 or 4 tokens, we can just batch these together and then have no waiting at all on the queue. So this will be faster. Every request will actually finish faster and will clear the queue faster. So just to summarize that, this is the full situation. If you don't query batch, some of your messages have to wait on the queue, and it takes longer to clear the queue, and they will take longer to return as well. And with query batching, it processes much faster. I also just want to give a quick shout out to staff engineer Chung Pei, who implemented this.
Cool. Thanks, Andrew. Yeah, so Andrew just discussed dynamic query batching, which is a technique to improve the overall system throughput without regressing the latency of any single small request. And so in the next couple slides, I want to explore another optimization that we've also done in our backend, which is a bit different. It's essentially, what if we have a large request of large batch size that is still latency sensitive? This is pretty common in reranking, where you get a large batch of examples and you want to do a final pass reranker optimization step to improve overall retrieval quality. And so if you send that large batch to a single GPU and do inference, the latency is not that great. And so unbatching is a technique to address exactly this problem. So instead of sending a single batch to a single GPU, we first break up the batch into smaller execution units. So in other words, we unbatch the large batch, and we send it in parallel, those smaller execution units, across multiple GPUs. And so the end result is that the latency observed by that single request is lowered. I also have a concrete animation that should make this clearer. But essentially here, we have a single request with multiple examples, and I have 3 GPUs ready to go to serve requests. And so we can split them into smaller execution units, and you can see how now the work is spread across multiple GPUs in parallel. And so the end result is that the latency observed by that single request is indeed lower. So here in text, we have a side-by-side comparison, a timeline of what would happen with unbatching versus without unbatching. We have some point numbers here just for the sake of demonstration, but essentially, with unbatching, we were able to achieve a 5-second latency for that larger request. But without unbatching, we would have sent that single large batch to 1 GPU, had 2 other GPUs left idle, and the observed latency would be much worse, 17 seconds. Cool, so just to recap, unbatching is a technique that we selectively apply throughout in our platform on latency-sensitive paths, for example, in the case of reranking. And then another nice property here is that we do so in such a way such that we're able to lower the latency observed by that request, but without compromising the overall system throughput by just changing exactly where the flops get executed. So I'll hand it over to Andrew.
Yeah, so now we can talk about documents, and this is going to be, for instance, for indexing databases, it's more throughput sensitive, tends to be longer running jobs. So first, let's define it. It's any embedding request, so not reranker, that is not a query. So if the batch size is greater than 1 or the token count is greater than 512. And these are throughput sensitive, but they also operate under a latency SLO because the API is synchronous. So yeah, so a big thing here is going to be autoscaling. So the thing is, traffic is really bursty, and these indexing jobs, people tend to send a lot of traffic for. And so we're going to have to scale that automatically to respond to the traffic. But just to demonstrate why, for illustration purposes, assume we have a single GPU and it's processing a token per second, and the queue is getting 1 token per second. So this is a steady state where we're pretty much OK, and we don't really need to do anything. The problem is, if we get a burst of traffic, like let's say, for illustration purposes, 10 tokens in this case, at time t equals 10, we'll have 90 tokens on the queue. And as time goes on, the queue builds up really quickly. It should be in rate minus out rate times t at time t. And so if you get a really big burst of traffic, the queue backlog can go really quickly, and then it can be hard to clear that without having an SLO violation. So that's really the crux of the problem. And so I guess you might ask, like, why not just allocate a ton of GPUs at the start? And the answer is it's really expensive. And the other answer is, if you can optimize your system well enough, you can actually meet the latency SLO. You can scale fast enough to meet the latency SLO. And the most important thing is meeting the user's throughput in time so they can finish their indexing job without too much delay. So if you optimize your system enough, you can do this. Angel will talk a little about that later. But yeah, so here's the autoscaling system, what it might look like. And so you have a queue for each individual model. I want to highlight here that for our backend, we're serving a bunch of different models that all have to share the hardware, all the GPUs. So in this case, we give each model its own queue, and each model has its own number of replicas. Model 1 has 6 replicas. Model 2 has 2 replicas. These are on GPU. And then we have these things called warm GPUs. So that's called the warm pool. And what happens is when one model needs extra replicas to meet its traffic, it's going to scale up into those warm GPUs. Those are left idle and just eligible to be scaled into in case somebody else needs to do that to avoid a latency SLO violation. And I also want to highlight that we have 2 autoscalers here. So one is going to help make those decisions about model replicas and determining how many replicas each model needs. And the cluster autoscaler is going to decide how many GPUs the cluster needs. So can we scale down to save money, or do we need to scale up because we're going to have more traffic spikes that we need to cover? And so the first thing is, how do you actually even make the decision to scale? And so to do this, we use basic queuing theory like we talked about earlier. So the queue has an in rate, it has an out rate, and it has a backlog at some time t. And also note that that backlog is usually given in messages, but in fact, for us, the most important thing is the number of tokens total, because that determines how much processing time we actually have. And so, yeah, so the algorithm accounts for the in rate, the out rate, and the backlog, and then makes a prediction about how those heterogeneous payloads, how long it will take to process them, and how many replicas each model will need to process their queue backlog. And it has to be intelligent just because the models are all sharing the same hardware. So we have to make sure that we do that properly and safely. And then the cluster autoscaler also has to decide if we need to scale up or scale down the warm pool, basically. So just to give a simple example, let's say there's a bunch of messages on Model 2's queue, and at the next time step, we dequeue 2 of them, but the queue gets even larger and the in rate's really high. So what happens is we have this data store that is the queue every some number of seconds. And it's getting the metrics like the in rate, the out rate, the backlog. And the model autoscaler checks in, crunches the numbers, and decides that we have to scale up Model 2. So it scales up into the warm pool. And then what happens is the cluster autoscaler might decide we need 2 extra GPU nodes because it might be maintaining an invariant, like some percentage of the active nodes has to be in the warm pool, or some absolute number of nodes must be in the warm pool, or something like this. And the last thing I want to highlight is we assumed here that the Model 2 replicas scaled up instantaneously, but in reality, it can take a really long time. And it's actually really hard to make this fast. So Angel's going to talk a bit about the pod startup.
Yeah, so Andrew was kind of alluding to this already, but yeah, Andrew just discussed autoscaling at more of an algorithmic and high-level infrastructure standpoint. But what this discussion takes for granted is just how long it takes to scale up a new GPU pod and have it ready to serve traffic. And in practice, what we've observed in our infrastructure is that in the worst case, when you're essentially cold starting a GPU pod, it could take on the order of several minutes to get this GPU finally ready. And as you can imagine, in an inference platform, this overhead is effectively unacceptable. And so optimizing this core primitive of simply just starting a GPU pod quickly is is important to us, particularly because a lot of our work tends to be, as Andrew was referring to earlier, tends to be very unpredictable, heterogeneous. And so if you have a slow pod startup, your autoscaling will also be slow. And so you won't be able to meet the unpredictable demand. So in the next couple slides, I want to just touch on it and touch on some optimizations we've done to make this pod startup much faster. So there are several steps in the pipeline to actually start up the pod. The core insight here is that the cold start latency is significantly dominated by I/O, and particularly disk and network I/O. And the reason for this is two steps of the pipeline in particular. The first is that you need to download the container images before you can run them. And then the second is that you have to fetch the model weights beforehand. And so in the next couple slides, I'll walk through how we optimize these two steps that were heavily I/O bottlenecked. So first of all, the container image downloading. So as Andrew mentioned earlier, we have a cluster autoscaler. And what it does is that it pre-caches the images onto the nodes in advance. And so this simple optimization alone basically takes the I/O downloading off the critical path, and it saves, in many cases, several minutes off the cold start time. So while it's rather simple, this is it's quite effective in reducing the GPU pod start. The second bottleneck has to do with model weights. And what we've done, or at least how we've formulated the problem, is we formulated it as a classical multi-tiered caching problem. With the idea, or like the core intuition is we want those model weights to be as close to GPU memory as possible so we can abuse locality. We've served many different models in production, so the model weights do start off far away from GPU memory, for example, object storage. But over time, as we reuse them, they make their way closer and closer to GPU memory. So perhaps CPU memory or disk, or perhaps at least in-cluster shared network storage. Our cluster autoscaler and model autoscaler are aware of this caching dynamic. And so across the optimization of image downloading and also model weights loading, we're able to take a heavily I/O-bound operation of starting up a GPU pod. And instead of it taking several minutes, it's now on the order of several seconds. So this is super impactful for us in terms of our ability to meet unpredictable demand across many of our different models.
Yeah, so thanks. So we talked about everything outside the GPU, but now we can talk about the actual inference engine itself, which is executing the code on the GPU. And for this, the first thing we'll talk about is something called sequence packing. So if you have a naive inference engine, what might happen if you give a batch to the inference engine is the sequences may have different lengths. And if you use a two-dimensional tensor for that, you have to actually basically pad those smaller sequences up to the length of the longest one. But those padding tokens aren't really useful. They're just there to make the shapes work, but they use as much compute as a real token. And this can be a really big issue. But as it turns out, most operations in the transformer don't depend on the sequence boundary at all, and the ones that do support just passing a list of the lengths of sequences. So what you can do instead is just pack it into a 1D list, and then you don't have any padding wastage at all. And this is really important because, for instance, for the dynamic query batching, if we didn't have this, we'd have to pay a lot of extra tokens for padding when we batch the queries together. Similarly, for documents, it would really negatively impact the throughput. So this is actually really important. Another thing is kernel fusion. So kernels are what are actually executing on the GPU. And if we look at what a kernel is doing, it might read something from the GPU and then output y, which is f of x, and then read y, output z equals g of y, if we're trying to compute the composition of these functions. But kernel fusion is pretty simple. You just, instead of doing those computations in separate kernels and doing two memory loads and stores, you just do it all in one kernel. So you load it once and then output it. So you load x and output z immediately. And the reason why this is helpful, well, to demonstrate that, I'll define arithmetic intensity, which is the number of math flops divided by the number of bytes transferred from memory. So it's a property of an operation. And if we do kernel fusion, we're probably going to be doing about the same amount of math, but with much less memory transfer. And so that increases the arithmetic intensity. What we're looking at here is a roofline plot. So it's showing performance of the operator in teraflops per second, so how fast you're doing the computation, versus the arithmetic intensity of the operator. And that is how many flops of math we're doing per memory byte transferred. And so one way to increase this is actually just to add more tokens. But if you have small token payloads like we do for queries, the other way to change this is to make the operator more efficient by fusing kernels, which just gives you higher arithmetic intensity, even at the same token count. So this is really important for queries and also helps with document throughput. The last thing is kernel launch overhead. So one thing to understand is that kernels are launched from the CPU to the GPU. And they're launched asynchronously. So when we launch a kernel to the GPU, the CPU gets control again and can launch the next kernel, for instance. But especially for small payloads, it can take even longer for the GPU to launch the kernel, for the CPU to launch the kernel than it takes for the GPU to actually execute it. And then you have a really bad bottleneck, and you really don't want this. You don't want to be CPU limited, definitely, if you're doing GPU computation. And so if that is an issue, one thing that you can do is something like coup de grace, which just makes the submission of the kernels to the GPU much faster. And some people also switch from Python to Rust. And so we've tried some of these optimizations as well. Yeah, I think.
Cool. Yeah, just to recap, so we first start off by discussing some of the core challenges we face when developing an efficient inference platform for embedding and reranker inference. And then we saw how different aspects of our inference platform work together to deliver low latency while maintaining high throughput. Yeah, thanks everyone for coming, and let's go get lunch.